in quiz 2, we asked you to solve this problem. We have a potential given in spherical coordinates. We know that electric field can be computed from the potential by taking negative of gradient of the potential. So find the electric field function using the first equation here. And then we are asked to calculate the electric field at this point, which is given again in terms of spherical coordinates, r equals 1, theta equals pi over 3, phi equals pi over 2. We are asked to draw this electric field vector. And then there's a reference to Gauss's law, which says the divergence of the electric field gives us charge density over epsilon naught. And we were asked to compute the divergence of the electric field to find the charge density. All right, let's get started. So part A, we have gradient. So now spherical coordinates, okay, we have the equation sheet. Gradient is taken in this way. So here we have no phi hat component, so we don't have to worry about this. So we need a partial with respect to r for the r hat, r component, and then partial with respect to theta multiplied by 1 over r for the theta component. Okay, so let's do that. So electric field would be negative gradient of v, which is going to be negative of r hat del r plus theta hat 1 over r del theta. And this operator will apply on our potential, which is given by 8 over r squared minus r times cosine theta. Okay, so what we have here is for the r component, I need to take the derivative of this. Cosine theta acts like a constant. So here I have del r of 8r to the negative 2 minus r. And then for the theta hat component, I'm carrying this negative carefully, minus theta hat over r. And then the entire thing acts like a constant, 8 over r squared minus r. Now I have del theta of cosine theta. All right, so let's go ahead and do it. Minus r hat cosine theta. This one is going to be minus 2 drops r to the negative 3. This one is going to be just 1. And minus theta hat over r, 8 over r squared minus r. Now, cosine theta, if you take the derivative with respect to theta, you get minus sine theta. All right. So this is minus, this is minus, this is minus. So I can just distribute this in, and I will get r hat cosine theta 16 over r cubed plus 1. And here there's minus, that's a plus, so plus theta hat. If I distribute this one, I'm going to get 8 over r cubed minus 1. Sine theta. So that's my electric field. All right, so in part B, we need to calculate this electric field function at r equals 1, theta equals pi over 3, phi equals pi over 2. Now, it's very easy. You just substitute r equals 1 and theta equals pi over 3. You'll get those. Now, one thing we should remember that r hat and theta hat also depends on these positions. I mean, for example, you might think phi hat is irrelevant. No, it is relevant because r hat and theta hat are not constant unit vectors. They depend on the position. So phi equals pi over 2 will help us determine what r hat and theta hat is. And in next part, when we draw the electric field vector, that will be used, okay? So for now, we can just write it in spherical coordinates. So I have cosine of pi over 3, 16 over 1 cube plus 1, plus theta hat 8 over 1 cube minus 1 sine of pi over 3. So this is 1/2, this is root 3 over 2. So if we put it all together, we can write this is 17 over 2 r hat plus this is 7 root 3 over 2 theta hat. So that's the electric field vector at this position. So to draw the electric field vector, consider this three-dimensional coordinate system. And now we measure phi from the x-axis pi over 2. So we are arriving the y-axis. And so then theta is measured relative to the z-axis, pi over 3. And then we measure 1 unit from the origin to find our point. Now, this point must be on the YZ plane, right? Because of the phi equals pi over 2. And in that regard, I should say this is the r hat, and then this is the theta hat unit vectors. So as you see, our electric field has r hat and theta hat, so that's how I need to think about the r hat and theta hat. So I need to first find the point, and once I find the point, r hat is always in the direction of the r vector, so this is my r vector. So, and theta hat is perpendicular to it. Why is it in this direction? Because it is measured in the direction of the theta, which is starting from the z-axis. It's 0 and then increasing this way. So that's theta hat. And if you are curious, if we had phi hat component, for example, r hat cross theta hat should be in the negative x direction in this particular situation, pointing into the page perpendicular to the YZ plane. So then let's go ahead and draw the electric field vector. So it would have 17 over 2, which is about 8.5. Root 3 is about 1.7 divided by 2. It's like 0.8-ish. 7 times 0.8, something like about 6. So this is a little less than this. So I need to draw this. And then a little smaller than that here for the theta hat component. But the total electric field would be the vector sum of those two. Okay. Now, this is kind of a rough drawing. If we want, we can substitute r hat and theta hat in terms of their x hat, y hat, z hat equivalents and find the exact electric field vector here in terms of x, y, and z. Okay. So that's our electric field vector. Although I did not ask in the question, it would be fun to express this in terms of Cartesian unit vectors. Let's do that. Now, we know we have, again, in your book, in Griffith, 4th edition, equation 1.64, r hat, theta hat, phi hat, they're expressed in terms of the respective theta and phi values and in Cartesian coordinates. So I'm going to use those. So r hat is sine theta cosine phi x hat plus sine theta sine phi y hat plus cosine theta z hat. So in in our case, we know r is 1, theta is pi over 3, phi is pi over 2. So if phi is pi over 2, cosine pi over 2 is 0. So this is 0. So there is no x component. And then sine pi over 2 is 1. Okay, theta is pi over 3. So sine pi over 3 is root 3 over 2. Sine pi over 3 here is root 3 over 2. And cosine pi over 3 is 1/2. You see no x hat component, no x component, y and z component only. So r hat becomes root 3 over 2 x hat plus 1/2. I'm sorry, y hat, no x hat, just y hat, and z hat. Okay, as expected, it's on the yz plane. Okay, now if we go to theta hat would be cosine theta cos phi x hat plus cosine theta sine phi y hat minus sine theta z hat. Again, given our values, r is 1, theta pi over 3, phi pi over 2. This is again 0, so no x component. This is 1. Cosine of pi over 3 is 1/2, right? And sine of pi over 3 is root 3 over 2. So that means for theta hat, I can write 1/2 y hat minus root 3 over 2 z hat. Okay. Now we can put them together. So this is what we had, 17 over 2 times r hat and 7 root 3 over 2 theta hat. So E becomes 17 over 2, substitute r hat for r hat, the y hat, z hat equivalent, root 3 over 2 plus 1/2 y hat plus 1/2 z hat, and then 7 root 3 over 2, 1/2 y hat minus root 3 over 2 z hat. Okay. Let's combine them together and get electric field in terms of y hat and z hat. So I have 17 over 2 times root 3 over 2, and then I have 7 root 3 over 2, 1, 2. So both of them 1 over 4. This is 7 root 3. This is 17 root 3. So 24 root 3 over 4. So E will be 24 root 3 over 4. So that's 6 root 3 y hat. Okay. 17 over 4 z hat minus 7 times root 3 times root 3 is 3. 3 times 7 is 21, but with a negative sign. 17 minus 21 is minus 4. Minus 4 over 4 is minus 1 z hat. So that would be the electric field y and z components, 6 root 3 minus y hat minus z hat. So it is not, indeed, it's not parallel to the y-axis. It's just tilting down a little bit because there's a negative z hat component. The y component is larger, definitely much larger. Okay, so that's part, again, an extra thing that I added here to give you a sense of what it is, and also showing clearly that E is for the given values of r theta and phi must be on the yz plane. Okay, that's that. The final part is the divergence. So divergence of E in spherical coordinates, it's given by the following equation: 1 over r squared partial with respect to r of r squared times the r component plus 1 over r sine theta, theta, partial theta, derivative and times of sine theta times the theta component. There is no phi component, so I don't have to worry about that. Okay, so let's write it out. 1 over r squared del r of r squared. Now remember, our electric field that we found was this. So it is r component is this entire thing. So I'm going to copy it there. Cos theta 16 over r cubed plus 1. So that's the entire thing. And then plus the theta part, 1 over r sine theta, partial with respect to theta, sine theta times. And there I have 8 over r cubed minus 1 times sine theta. 8 over r cubed minus 1 times sine theta. Okay, so let's do this. So cosine theta here acts like a constant, so I'll pull it out. Cosine theta over r squared. Now I'm going to take the derivative with respect to r. This is 16 times r to the negative 3. This is just 1, but they are multiplied by r squared. So I'm going to have del r of 16 times r to the negative 1 plus r squared. Now the theta part, 1 over r sine theta, 8 over r cubed minus 1 is like a constant. Sine theta times sine theta is sine squared theta. So this is sine squared theta, partial with respect to theta. Okay. Now go ahead and take the derivatives. Cosine theta over r squared, 16r to the minus 1, going to be 16 minus 1 drops. We're going to subtract 1, so it's going to be 16 minus 1, minus 16 times r to the minus 2. This one will be plus 2 times r. Plus, now here I have, I can put r in the inside here. So it's going to be 1 over sine theta, 8 over r to the 4th minus 1 over r, right? And then this derivative will be 2 times sine theta. Now, first I take that, and then derivative of sine theta with respect to theta, I'm using the chain rule, obviously, cosine theta. Now, this sine theta cancels with this. So let's put the remaining things. Cosine theta negative 16 over, if you substitute this, 1 over r to the 4th then, plus what I have here, 2r over r squared, so it's going to be 2 over r, plus, now again, I have another cosine theta, I have a 2, so it's going to be cosine theta, and if I distribute this to 16 over r to the 4 minus 2 over r. Now we see a lot of similarity, right? Cosine theta. This is negative 16 over r to the 4. This is positive, and this is 2 over r. This is negative 2 over r. Looks like we're getting a 0. So cosine theta in parentheses, so I'm getting minus 16 over r to the 4 plus 16 over r to the 4 plus 2 over r minus 2 over r. Indeed, all cancels. So that's 0. So that means del dot E equals to rho over epsilon naught is 0. So the charge density is 0 for the geometry in which this potential was solved. Okay. All right, that's it. I hope you enjoyed the solution.